Welcome to the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. Today on the podcast, I'm talking with Hari Balakrishnan. Hari is a professor at MIT and the founder and CTO of Cambridge Mobile Telematics. Telematics is all about collecting data about how people and vehicles move. And it's really important if you want to understand motion patterns and movement patterns. But I'll let Hari talk more about this in a lot more detail in just a second. Just before we get started, I just want to mention at the start of the episode, during the episode you might hear me say telemetrics instead of telematics. That's a mistake on my behalf and I apologize for the confusion. Hi, Hari, welcome to the podcast. It feels funny saying that after we've just been talking for the last 5 minutes, but welcome. It is honestly, it's great to have you here. I'm looking forward to the conversation. As a brief introduction from my side, you are the founder, chairman, and CTO of something called Cambridge Mobile Telematics. Why don't we start there? Could you give me a brief introduction, please?
Yeah, so I'm the founder and CTO and chairman of CMT, Cambridge Mobile Telematics, whose mission is to make the world's roads and drivers safer. We introduced our first product about 12 years ago using sensor data from mobile assets, phones, and IoT devices to understand how people drive and provide incentives to make people safer drivers. So that's what our company does.
If you don't mind, I'd like to start right at the start. What is this kind of data that you're collecting? Could you just describe it for me, please? I hear these words sort of banded around all the time, and I don't know if I have a really good working definition in my head. So what is telemetrics?
Telematics is the idea of collecting data about how people move or how vehicles move. So principally, the data includes factors like the acceleration, the braking patterns, the speeds, and the types of places that people drive in order to understand how risky somebody's driving is, and then providing feedback and incentives for them to become better drivers. So the type of data would include things from velocity and position sensors, accelerometers, gyroscopes. And when you take all of that data, often overlaid on maps, you can use that to understand driving patterns, understand what causes crashes to happen, and then provide information and feedback to people so that they avoid those risky adverse behaviors and they become better drivers, benefiting them, benefiting society. That's really what we do.
When I think about that kind of data, are we in reality just talking about people having cell phones in their pockets and you getting access to the data? Is that enough, or is there different sensors involved, maybe on the vehicle themselves, or is a cell phone enough to collect this kind of data?
That's a great question, Daniel. So it turns out that the platform we built, it's called the Drivable Fusion platform. Fusion is because it is, in fact, important to have the ability to process data, collect and process data from a wide range of sources. So cell phones alone are enough if the primary focus is on behavior of users while they're driving. Because what the phone does is it's pretty much attached to your body most of the time. And so it is possible to process data, collect data in the background with the user's consent and process that. And we can understand how you drive independent of the vehicle. But then that's not often enough. Often you want to be able to understand the risk profile of particular vehicles. And often you may want to also only measure somebody's driving patterns when they're in vehicles that they own, as opposed to, say, when they're in a cab or something like that. So what we advocate is using a platform. It processes data from phone only, or it could be phone together with IoT devices. Like we have a drivable tag. We've shipped over 40 million of them. It works in concert with the phone. Or it could be IoT devices alone, including aftermarket devices, for example, used by many fleets. Or it could be data from the vehicles, connected vehicle data with the user's consent could also be used. Now, it's important to understand that when you collect data from the vehicle, you don't know much about who's driving or the specific behavior of a driver. So if you and your partner both drove a vehicle, with the vehicle sensors alone, it would be hard to provide feedback to you and your partner, different feedback. You might drive in a certain way, the partner might drive in a different way. If you have a phone, of course, I could provide feedback. You could provide feedback pertinent to that user of the phone, but you don't often know which vehicle they're driving. I mean, sometimes you do, but often you don't. We provide a platform that can do purely behavior, purely vehicle, or uniquely a combination of vehicle and vehicle and driver. So it's all of the above. And we have a mantra which is no data left behind, no user left behind. So we go where the data is, and we're able to take whatever data is available and provide the best possible insights. Some pieces of data have more insights that are attainable, and some have less. But every piece of insight aligned to the mission of improving safety is valuable and useful.
Yeah, so I like that. No data left behind. Brilliant. That being said, there must be some data that's more useful. And so, and maybe we could start the conversation around this, thinking about what's more important, the I don't know, the absolute positioning of this, like where is this device relative to other objects in the world, or is it more like in general we know that the movement pattern looks like this?
Yeah, the latter. The latter is much more important. The pattern of movement together with the context in which that movement's occurring. For example, knowing that somebody is driving at 120 kilometers an hour is useful, but knowing that they're driving at 120 kilometers an hour when everyone else is driving, or on average, people are driving at the same time at 90 kilometers an hour, that's incredibly important to understand. At the same time, here's another one. Let's say the speed limit is 100 kilometers an hour and somebody's driving at 120. If everyone else is also driving at 120, that might be fine relative to the risk profile. And so it is important to understand motion patterns or movement patterns, but do so contextualized in the environment in which people are driving. And that's actually a place where the maps, when available, play a critical role. But it's not just the maps as a static entity. We believe very strongly in dynamic maps. What I mean is overlaying on the geometry of maps contextual information about movement patterns, about risk patterns. That's what is maximally valuable.
So you need the maps. It almost sounds like you're using them to ground truth the data. You have this pattern data, and then perhaps you use maps to, and correct me if I'm wrong, please, to ground truth the data. What's happening in this context in terms of the known geometries, perhaps of road lanes, just as an example. But then you layer on the data to this. So that makes your data more accurate. Is there any sort of feedback loop that brings your data back into the maps, making the maps more accurate?
Yeah, absolutely. So, firstly, I would say it's not so much about ground truth. It's much more about taking the map geometry data and layering, as you mentioned, layering on dynamic context. So, layering on things like what's the distribution of speeds observed on particular roads, and then using machine learning to produce what we call road risk maps, which is providing a rate of risk, a rate of crash for every road segment on the planet.
Wow.
Even if we have not seen crashes on that road, there is still an extrinsic underlying rate of crashes that every road experiences. And being able to use similarity patterns with other types of roads in a similar context to provide that geometry, that dynamic information on top of road geometry. But then, because we know patterns of driving and where people are driving, we can and do, in fact, use the data to correct maps. For example, we routinely correct speed limit information
Mm.
because people complain when we tell them that they're driving higher than the speed limit, and when enough people complain, or we now have machine learning that autocorrects some of the map errors in speed data. There are places where we can tell how many lanes there are on the road just by the pattern of turns and straight driving. We can infer things that about where people are stopping, for example, on roads. So it is possible to correct maps, and certainly geometric corrections are also possible, where we find that it turns out the map didn't have certain patterns of driving, ways in which people drive, but there's enough people driving that you could use it to say, you know what, the map was probably erroneous.
Mm. Well, what about, I'm not sure if you mentioned it there, but connectivity. I can turn this way. And I'm thinking about the things we miss in satellite data, for example, a bridge and overpass. We can't see from a satellite image easily or aerial imagery easily how those two roads, when they cross over each other, how they interact with each other, where I can turn right, where I can turn left.
Yeah, I think that GPS traces are used in research and industry to to draw those inferences about what turns are allowed. And in fact, it's not just about what turns are allowed. If you in many places, roads are 2.5-dimensional or 3-dimensional structures because you have overpasses and underpasses. When you look at imagery, sometimes it's difficult to figure out whether two roads in an image are connected or whether they're layered on top of each other. And by looking at ways in which you find that people drive in a certain way and then drive onto another road, but at the same time, they drive in a certain way and they cannot get onto a segment that looks like it's connected. It might often be that it's higher or lower. So telematics data is useful in drawing those inferences that imagery alone might not be sufficient. Conversely, imagery allows us to draw inferences that cannot be obtained from the GPS data. So both of them are valuable.
What could they be?
Imagery, for example, I mean, this is related to some research that we did over at MIT. Imagery can be used to draw inferences about maps when you don't have much driving happening. So there are parts of the world where your data might not have enough people driving for you to draw inferences about what's happening there, and imagery could be used there. Also, given the precision or lack of precision of consumer GPS devices, such as on your phones, imagery can be used to draw inferences about the number of lanes on a road. Even when the lane markers are not clear, you can actually draw inferences about the width of roads and the lanes, number of lanes on a road, inferences about right only or left only turning lanes that are visible in markings from images. But the data itself might not be clear cut on that. Imagery can be used to draw inferences about whether there are bicycle lanes, whether there's a protected bike lane, whether there's a pedestrian crossing, or whether people are just walking across the street. So they complement each other, and they're both actually critically important in the process of building maps. But the work that we do is largely about adding dynamic data to maps. We view maps as not a static geometric thing. We view maps as continually evolving in time, not only because planning changes and infrastructure changes, road infrastructure, but also because the vehicles, the people on the roads change with time. And we think that layering dynamic information on maps provides tremendous value.
What kind of time windows make sense to talk about when we talk about that? Because real time, there was an accident just here now. Does that is that the metric you want to tell people about? Does that dramatically impact your risk map of this area?
That's a great question. I think that there are companies, Google Maps, Apple, Waze, et cetera, that are now pretty good at dynamic traffic information, real-time incident information, and so on. The work that we do is over a little bit longer time scales than that. It's asking questions that are also equally important, such as how risky are these roads? And how does that risk change dynamically, either because there are incidents or because there's a level of risk that ebbs and flows with time as traffic patterns change? But as people drive on those roads, what is the actual extrinsic level of risk caused by the patterns of mobility? And then coming back to the individual, what can they do to improve their driving performance, both by becoming more aware of their driving, but also by understanding better the context in which they're driving. As one example of this is there are roads where there's higher levels of phone distraction than others. And often this is driven by suboptimal infrastructure.
Mm.
It's driven because directions are very confusing. And so people then are much more focused on their navigation apps. Even people who are very familiar and live in the area. Boston has a number of examples like this where I've lived here 25 years. I still get confused in certain places because sometimes there are changes, but sometimes it's just confusing. And we know places where people are much more distracted. And that's not something that is visible in real-time crashes, but it's visible in a lot of near crashes and a lot of confusion, but above all, higher levels of distracted driving.
Can you see that kind of information or make those inferences directly from the data, or does it, okay, something happened and then you do some further research and find
No,
out?
we can draw it directly from the data.
Wow.
And we built these models now that use the sensor data to directly draw inferences on things like higher levels of distracted driving, higher levels of hard braking. You can even do things like correlate that with, I'll give you a very concrete example. You find that there's a higher level of hard braking, a rate of hard braking that happens at certain intersections at certain times. And you could overlay that with information about bus routes, public transit bus routes, and find that, well, whenever there's a bus that hits a bus stop, maybe the bus stop is too close to an intersection. That does happen. And that leads to poorer visibility for drivers, causing a higher rate of hard braking. So in other words, over the entire day, on average, you don't see a lot of difference, but there are particular times when it peaks or increases. And it's correlated with this external context of when the buses show up.
Yeah.
And then you can get this data and work with the city to change the infrastructure, to move the bus stop,
Yeah.
or to provide better signage. There are times we find when there are certain places like the Longfellow Bridge in Boston, connecting Boston to Cambridge, where people are much more distracted on their phones. It's because it's confusing. When you come out from Cambridge heading into Boston, it's really hard to figure out which lane to be in. And it's just something where even people used to the area sometimes are confused and they're looking at their phone more, which means there is an elevated degree of risk at certain locations. And that's a place where the city could put up signage that says, or clarify the signage on directions, but also put up signs that say, put your phone down.
Which would be a good idea anyway. I
Which would
want to
be a
talk
good
about infrastructure in just a minute and what this kind of data means for infrastructure projects. But I want to go back to this idea of deriving information. I know speed limits are really tricky. Like it's really difficult to get accurate speed limits, accurate speed zones. Can you derive that from the data that you have?
We don't directly derive speed limits. What we have derived very successfully in our technology and our science is an estimate of the safe speed zone. In other words, what's the speed above which risk is high, risk of a crash? So there are cases when the speed limit might be 55 miles an hour or 110 kilometers an hour, whatever the number might be. But the actual risk speed is 70 miles an hour.
Yeah.
And so we do know how to draw those inferences. As for the actual speed limit automatically, we have some technology to do that, but we're much more focused on where does the risk of a crash start to elevate and making sure people don't exceed that. And of course, they shouldn't exceed the posted speed limit, but you and I both know that that's what is the phrase? More honored in the breach than in the observance.
Given this sort of insight you have and the access to the data you have, do you see different cultures, like people driving in like vastly different ways when you look across your entire data set?
Yeah, people in different countries drive differently. In fact, I call it driving culture, and it actually is regional as well. People in different cities do drive differently. The observance of speed limits, observance of rules is very different. And we've helped understand this. For example, when states pass laws against distracted driving, phone distraction, and distracted driving, for example, the state of Ohio passed something about a year ago, and we were able to find a noticeable improvement in reduction in distracted driving. And the governor actually tweeted about it with our data, where we were able to show that there is a reduction in distracted driving. Now, there is a possibility that it would regress to what it used to be, depending on enforcement, depending on public awareness. But there's absolute differences. We see differences between cities, and we do see differences between not only between countries, but between places within the same country.
Wow.
And I think a lot has to do with culture. We find that observance of speed limits is unsurprisingly a function of enforcement. And enforcement is not uniform. It's hard for it to be uniform. And so we do see tremendous differences. And my company, my colleagues published a paper at PNAS, the Proceedings of the National Academy of Sciences, a very prestigious journal, on this result that looks at a handful of US cities, maybe 10 to 12 US cities, and finds that the observance of speed limits is highly variable. But more importantly, when you correlate this with traffic tickets, well, tickets are given where the enforcement is.
Yeah.
Tickets aren't given where the infractions occur. Infractions are more likely to occur in places where there is poorer enforcement. But because enforcement it's not easy for it to be uniform, we find that the impact is non-uniform.
Again, like, can you see this in the data? Because I'm thinking you're just saying it's not uniform now. So it must be difficult to pick up that pattern and say, oh, this new thing that we're seeing in the data is because enforcement is happening here. if it's 3-4 days of enforcement and then it's gone again and it moves somewhere else. I wonder if it almost looks like noise in your data set.
That's a good question. It doesn't look like noise. It does look like when this happens, it's not that the process of, for example, enforcement or new laws, it's not a noisy process. And the timescale over which it lasts is, weeks.
Mm.
So we find that the changes that occur, the timescale of those changes, it lasts for a while. And of course, it changes over time, but it's not a random noise process that you cannot observe in the data. I mean, again, I'll go back to the anti-distracted driving laws. When the laws are enacted and there's public relations, publicity around it, we definitely see a positive impact. In the same way, we see an impact with our own programs and users. When suitable incentives are provided, users respond. We have one of our customers in South Africa, Discovery Insurer, who run the Vitality program. The crash rates that they observe on their users are 24% lower than the rest of the population of the country. That's a fantastically positive result because of incentives. And again, people respond to carrots and sticks.
Yeah.
But neither carrots nor sticks are completely arbitrary, random, stochastic noise processes. I mean, they're performed by human beings and they sustain for some period of time. And therefore, the impacts of those are seen in the data beyond just random noise.
We talked briefly about infrastructure. I mentioned infrastructure before. Could you model if I put a speed bump on this road, it would have this impact?
Oh, brilliant question. This is exactly the research project that our scientists are working on now. We have some a strong PhD student from MIT working on it with our R&D group, and they have a wonderful result. It's as yet unpublished. We're hoping to get it published. This group, they've been able to predict the what if question. What if I put a speed hump or speed bump at a location? What if I put a stop sign? What's the impact going to be? And the way they're tackling it is beautiful science. So the state of the art for how to do this is running very detailed simulation. So you simulate vehicles, you simulate the demand matrices of where people are driving, and you have to do this very kind of precise simulation. It's very difficult to do the simulation because real world mobility, just like simulating the internet is virtually impossible to high fidelity, simulating rich transportation network, road network it's very difficult to get high fidelity. The beautiful thing about machine learning is that these modern machine learning techniques have allowed us to perform what are called causal simulations. Causal simulations are intended to answer questions of what if I made a particular change? What is the impact going to be? And you can do this without classical simulation. You can do this now because any improvement, any change you want to make to a particular road, with enough data, there are other parts of the city, state, country, or world that look similar that have already introduced the mechanism you're trying to introduce in a place. And with machine learning, you can essentially detect what are the places of the city, country, state, or world that are most similar in pattern to the mechanism you're planning to introduce. And using essentially a variety of neural network technologies, we're able to make these types of predictions. So my colleagues at MIT have shown this for applications on the internet. For example, they've been able to show that when you apply algorithms for determining the quality of video, like what we have, or audio on this conversation right now, the quality of audio adapts to changing network conditions. And when you introduce a new mechanism for audio or video, you need to know in advance what it's going to do. And machine learning with this causal sim approach has been used for that. So we've applied that type of thinking now to road transportation, and we're really excited about the results. We're able to predict things like if you introduce a speed bump, what will happen, so that the cities can now undertake this, answer this question without introducing the speed bump, which are going to have a lot of impacts, right? Not only is the speed bump, you have to understand the safety impact, but you also have to understand what does it do to traffic.
Yeah.
And right? Because it's not just about safety. And when you have additional traffic slowdowns, that could increase the level of risk.
Yeah, that's exactly what I was thinking. Like, so let's say the risk dies down in one area and you just push the problem somewhere else.
Yeah, that's why these are hugely complicated problems, but that is exactly what we're working on. And, we have now data from 45 million users
Wow.
over the past 5 years, and a huge variety of real world conditions that allows us to ask and try to answer these types of what if questions that are fundamentally important to improving our safety, which ultimately the carrots are one thing, they're valuable, the sticks are one thing, they're useful. But if we can start changing infrastructure for the better, especially as vehicle technologies and the interaction of drivers and machine changes, that could be hugely beneficial. And I think the interaction of driver to machine is very important here because these vehicles have become very complicated. They're computers on wheels now. So it's now no longer the case you get in and you have to worry about the steering wheel and the brake and the accelerator. You now have to worry about lots of stuff, including your phone, the messages that you get on your phone relative to even navigation. And then you have this entire IT system in your car that you're mucking around with while you're driving, the infotainment system and everything else. And then you have all these ADAS technologies in the vehicle. It's become a lot harder to drive a vehicle, honestly. There's so many things you have to worry about now with technology in the vehicle. I think they're all good, but right now we're in a position where vehicles actually are more complicated to drive than 40 years ago.
I want to get back to that later on. I think we should save it towards the end of the conversation because I think there's an inch. I really want to hear your thoughts around, does all of this stuff get harder, better, easier, faster when we move to a world where it's semi-automated or completely automated in terms of vehicles? But save that for the end. I want to ask you a question about patterns. You said, okay, you can model these patterns. My guess is you also take into consideration the cultural patterns when you're saying, oh, I can see a city over there has implemented this, that, and the other thing, and that's the same as here. So not just the physical patterns, maybe the volume of traffic, but also the cultural, the driving culture in that area.
Absolutely. The driving culture in our data is manifested in terms of rates of hard braking, the type of hard acceleration, the type of speeding patterns that you see, and how that is contextualized relative to the aggregate traffic. What are people driving at relative to speed limits? Simple things like, do they stop at stop signs or do they do rolling stops? How do they react? So the data tells you all these things. We don't sit around explicitly modeling it by hand. We let the data tell us these things. And the pattern matching looks at what driving patterns and road geometries are most similar to the place where you're trying to make the remediation or the intervention, and answers the questions that way. So ultimately, it depends on having enough scale and fidelity of data. And that's the way these mechanisms can work. And once you have enough scale and fidelity of data, this approach beats classical simulation where you're essentially modeling every car driving on every road. Like, the analogy I sometimes draw is it's like counting every angel that dances on the head of a pin. It's very difficult to get it right.
I'm going to remember that. It's good. You mentioned earlier that carrots and sticks, and then we're talking about infrastructure, and it almost felt like the infrastructure is neither a carrot or a stick. It's the environment that these things happen in. Is that the way you look at things as well? So when we talk about modeling things, we talk about modeling the environment in which these behaviors are happening, and not essentially like a punishment or a reward.
Yes, I think fundamentally infrastructure is about changing the baseline rates of risk. But I think there is an aspect of behavior in infrastructure changes, particularly when it pertains to digital signage, which is part of infrastructure. So many countries, many cities have signs on the highway that remind people to fasten their seat belts or remind people about something or another. They sometimes tell you about an incident that might have happened. But I think we can extend that idea to places where we do see higher levels of certain adverse behaviors. And, with a little message, maybe even a funny message, remind people that the Instagram could wait. That sort of thing could be very helpful. It's a big sign that says something. And I think I've seen this be quite successful with advertising. You see billboards on the side, a lot of them are digital. And I think that road infrastructure could embrace those technologies, which, by the way, the digital aspects of those have become quite inexpensive.
Mm. That would be really interesting, actually. If you know a lot about risk, So you could, in just the same way, when we think about marketing, it's all about personalization. So you could say, look, in this area here, flash a sign saying, this is the thing you need to be aware of today, kind of thing.
Exactly right.
Mm,
Advertisers have done a brilliant job with figuring out a lot about what signs work on the side of the highways, and a lot of them are digital.
mm,
I see no reason why infrastructure can't adopt the same thing. And the data now, we and some others have the data now that can be used to make a societal impact for the better by providing behavioral messages that are not intrusive, that are just sort of, it's very clear that there are certain places where people are speeding a lot more than they should be. And you're not penalizing them, you're not giving them tickets, you're just reminding them.
mm.
And I think these could be very, very powerful. And you could adapt this to the context. In bad weather, you could provide certain information. You could provide information at specific times of day. That's
Yeah.
between 5 and 7, there's more phone distraction. You could tie this in to even things like, here's one example. You could tell from the data at what times of day there are people who've never driven on that road before or who rarely drive on a road
Wow.
versus frequent drivers. And when the rate of new drivers who don't often drive on that road is higher, you could provide mass information that's a little more tuned to the non habitual driver. And then at other times when people are driving as a matter of habit, it's a commute driver, some of them become very complacent
Mm.
because they think tomorrow is the same as today, is the same as yesterday, but there is a change.
Yeah.
And you could provide reminders that say, yeah, we know that you need to get home, but you know what? It's better to get home safe than sorry. So there's lots of opportunity.
It's funny, we like you mentioned before, marketers have done a great job with that, and we seem to comfortably embrace this idea that people have my data in order to sell me some socks. And why can't we do it for something infinitely more important when we talk about human lives and safety?
And we don't need your data. There's none of this data needs to be, uses your identity. It's highly aggregated information that looks at the distribution of rates of speeding, rates of distraction, rates of hard braking, etc. All of this data is completely anonymous, completely aggregated, and it's just looking at aggregate rates
Mm.
of adverse behavior. And we could also congratulate good behavior. Like we could give prizes to the, I'm just spitballing here, honestly, but you could pick drivers at random who are, if everybody's driving safely on a stretch of road, you could give rewards to people. I know sometimes it's hard to give rewards to random people, but maybe there's some incentives that people would offer. Like maybe some people could be given a little bit % off their fuel. And there's lots of opportunities here that when you combine marketing ideas with infrastructure improvements on safety, with the type of data insights we can provide,
Mm.
there's sea changes we could make. So I'm getting to this whole question you asked about, is infrastructure just something boring that you have to improve? No, I actually think exciting behavioral improvements with incentives and marketing oriented themes rooted in aggregate anonymized data could make a huge difference.
I don't know if I'm relieved or disappointed that you didn't say cryptocurrency somewhere in there when you're talking about
Yeah.
rewarding people. I thought, this is the
Well,
moment. This is the Bitcoin moment. He's going to say it. But
yeah,
no.
that might need a couple of glasses of wine.
Fair.
Well, I'll get there.
But not before driving, right? Not before driving.
Not certainly not before driving.
So a while ago, right around the time we're all talking about big data, we're also talking about smart cities. Have you seen this stuff come to fruition? Because I think that, with the kind of data that you're talking about, and then combining that with the sensor network and these sort of smart cities idea, that seems like a
Yeah.
really magical combination. But have you
Yeah.
seen any of that, or are you working with companies? Are you involved in that in any way, shape, or form?
Yes. So let me first preface by saying smart cities have been 3 to 5 years out for the last 20 to 25 years.
Yeah.
However, and I've been a part of the excitement of it and part of the group that's been tremendously skeptical of this in the past. That said, I actually genuinely believe that we will see far smarter cities with a lot of this technology in the next 5 years.
Mm.
And we are actively working on it. I know others are as well. But I think the reason why the time is ripe now is threefold. First and foremost, I think that now a lot of aggregated anonymized data and deeper understanding exists in order for us to start drawing inferences. Second, I think that the classical approaches to doing this, relying on particle simulation of vehicles, etc., just doesn't work. It's too complicated. And I think that advances in AI using this type of sensor data make it possible to do this type of thing. And third, I think that since 2017, vehicles have been laden with safety technologies. They just come out with more and more technologies. There's been a 250% increase in investment dollars in assisted driving type technologies in vehicles over a 5-year time frame. And this is interesting because not just 250% more vehicles have it. It's that there are far more vehicles that have it because the cost of these technologies has actually come down. So 250% on 10,000 vehicles, it's not the same 10,000 they've had more investment. There's a lot more vehicles that have had it, but more than 250% because the technology itself has come down. But yet, if you look at the same 5-year period, we've not seen much of an improvement in crash rates. And one of the reasons for that is that the interface between human and machine and infrastructure has become actually more difficult. So I think that the time is ripe. I think people have now really gotten serious about trying to make an improvement in safety. We've seen the impact of this with things like insurance telematics programs where we can drive crash rates down. So I think there's now starting to be more of a belief that these technologies can help. And using it to improve infrastructure, because of these three advancements, the access to aggregate anonymized data, the advancements in AI and machine learning that allow us to answer these questions that previously and draw these insights that previously were not possible. And third, just an appetite now that, all right, we put all this investment in technology, it's time to start influencing policy and making improvements. So I think that DOTs, governments around the world are starting to see this. So I do think that despite it being the next 3 to 5 years for the past 20 plus years, I remember presenting some of this from my academic research in 2005, saying in the next 3 years, we're going to see this. We did research like that. But I do think the time is right now because I think the technologies hadn't yet reached the level of capability, but now they're almost there.
It's really interesting to hear you say that the interface between machines, humans, and infrastructure has gotten more difficult, more clumsy, because the promise is that it's going to be more fluid and there'll be a lot of decisions made for us and things will just happen. How has it gotten more difficult, do you think?
Well, there's many examples. I think that we have infotainment systems in vehicles now. Pretty much every vehicle for the, certainly since 2017, 2018, if not earlier. They're not easy to use. And I know it's a hard problem, but if you look at, and then, you have CarPlay, Android Auto, you have the vehicle's own systems, but nothing is a single flake. The voice interfaces aren't there yet. I mean, they just don't work very well because the acoustic environment is very challenging.
Yeah.
And none of them enters into a dialogue with you. Now, I think that you can get to that. We will get to that point because AI has now advanced. But the result of it is that sometimes even finding or making the car do simple things is more complicated. Using a navigation system that's embedded in your vehicle, even if it's through your Google Maps or Apple or whatever, through CarPlay, is not that much easier than opening your phone and picking it. And the interfaces are, it's complicated because, from time to time, CarPlay stops working. It breaks the connection and it forgets my phone. This happens routinely on my car.
Yeah.
For whatever reason, the technology is not yet seamless. And if you now get to ADAS, you find that I often find I have this automatic lane keeping system in my vehicle. It makes me stick to my lane. But sometimes I want to change the lane. I know I'm doing it right, and maybe it doesn't quite understand. It's pulling me back. And I am almost literally wrestling with the steering wheel of my vehicle to make the change I want to make.
Yeah.
This is not a smooth interface. And this happens pretty much every time I drive. It's not like some unusual event. And a bunch of people react to that by turning it off.
Yeah.
Because they don't want to deal with it. And when you turn it off, arguably it makes it different.
Yeah.
I'll give you another example. We've done this study where we look at EVs, electric vehicles with ICEs, internal combustion engine vehicles. And a lot of the electric vehicles have very advanced ADAS technologies because they're newer vehicles. And we find that when people get used to driving one of those more modern vehicles, say a Tesla, which is really good in many respects, and then they drive an older or a different vehicle, they become worse in the other vehicle.
Mm.
They become worse compared to the average driver of the other vehicle because they get used to certain features. I mean, I have the same thing. I have two vehicles in my family, and one of them is newer than the other. One is 5 years old, the other is 3 years old.
Mm.
But the 5-year-old vehicle has some things the 3-year-old doesn't have, and the 3-year-old vehicle has a whole bunch of things the 5-year-old vehicle doesn't have. They're different makes and models. And I do drive them both. And it takes me a while to figure out that, you know what, the blind spot monitor is different in this vehicle from that. And you know what, this is the vehicle that actually does my lane change this way, and the other vehicle beeps differently. There's more stuff to worry about. Whereas earlier, I'm not saying those earlier vehicles were safer, but I had to worry about three things: the steering wheel, the accelerator, and the brake.
Yeah. Yeah.
And it was a marvel of human machine interface because anyone could learn to drive and be a reasonably good driver. The technology wasn't there. I'm not saying the technology is bad, but I'm saying the technology is not fulfilled its potential because of the human machine interface being more complicated. And we are 100% reliant on our phones in our vehicles because it has all the apps we need for driving.
Yeah.
And the interfaces are complicated.
Yeah.
Now, I think this will all get better, but I think it would be a tiny minority of people who think that these are easy to use.
Yeah. You make some really, really great, valid arguments there. But you also mentioned the interface between machines, humans, and infrastructure. So how do you see us interfacing with infrastructure in the future?
Yeah, I would love to see infrastructure that is informed by driving patterns and mobility. I'd like to see a more flexible infrastructure with digital signage and where we can work with use data informed decisions based rooted in insights from data to drive decisions on improving safety and efficiency. So in other words, intervention should not be where people complain the most. Intervention should be where the data indicates that the bang for the buck is going to be the highest. Yeah, I don't want to put a stop sign because the people living on that road are complaining about something. It's maybe fine we want to react to people, but it needs to respond to where the risk is the highest because the amount of money to spend on infrastructure improvements is not just finite, but it's not plentiful. Decisions rooted in insights from data, driving infrastructure changes is the way to go. And I think we will make dramatic improvements in safety if we understand that that is the way to deal with complex dynamic network systems.
Yeah. That makes a lot of sense. And I guess it gets right back to the conversation we had earlier about this integrating marketing into this. We could nudge people based on the data, and then the infrastructure would update given the current, I don't know, driver situation, volume of traffic, level of risk, whatever.
Exactly. And I think there's a variety of ways infrastructure itself could interface with vehicles. People have talked about, V2I, vehicle to infrastructure connectivity. And I think those, are theoretically good, but scaling those to the whole country, whole city even is quite challenging. And I don't know whether that will happen in the near term or not. But we don't need to wait for that type of real-time V2I integration to happen because a large number of good decisions can be made over timescales longer than hard real time.
Yeah.
There are a lot of these things we have weeks or months of data that can be used to make perfectly informed decisions about signage, about changes to design and changes to the implementation of infrastructure.
It's a lot to digest. I appreciate your insights in this. I want to move on though, and I want to talk about autonomous vehicles because it's exciting. And I'm curious how that changes things. Does it change things dramatically? Do we need more or less of any of these things that we're talking about? Is the collection of data going to play such a ginormous role as it does today? Because it's a given that these things will be collecting data and that they will have the infrastructure to communicate with each other, to perhaps better communicate with the infrastructure as well.
That's a great question. I think that AVs are certainly exciting, and I suspect that within 10 to 15 years, maybe 15 years, we'll see a good chunk of vehicles on the road being mostly autonomous. I think that there are parts of the world where in order for AVs to successfully get deployed and scale, we do need to change the infrastructure. That might be dedicated lanes for AVs, perhaps, or it might be more fundamental changes that allow for a mix of AVs and non-autonomous vehicles, not just cars. I actually am referring to bicycles, pedestrians, two-wheelers, motorcycles, etc., coexisting, and understanding the culture of driving. The AV technology that would work in Mumbai or Bangalore or Chennai in India or Delhi or whatever might be quite different than what works in Shanghai, and maybe that itself may be quite different from what works in New York, and of course what works in San Francisco. These are all different. I mean, what works in rural Texas or Illinois is likely different from what works in Singapore, because the culture is different, the way in which these places operate is different. So I think we will see I think that we're going to have to localize and make some changes to infrastructure. I think that understanding for AVs to understand intent of people who are not computers would also be valuable. So I have a feeling that this type of data that we have obtained insights with about what constitutes the best human drivers, I think that the best AVs would be ones that drive like the best human drivers in a world where they have to share roads with humans. So this idea that you can react in 10, 20 milliseconds, therefore you should, is problematic because humans don't react that quickly. So that might just lead to situations where we see a lot more rear ends that human beings driving behind an autonomous vehicle hit them because the AVs can react far more quickly. And I don't think that's the right approach. I think we need to realize that we're going to be in a hybrid world for quite some time, given the median age or even the average age of, certainly the average is higher than the median. The average age of the fleet of a vehicle on the road, it's more than 12 years. And so we're going to have to share the roads. So I think that ultimately data is going to drive a better design of future vehicles.
When you think of the hybrid world where humans and machines need to share the road, do you think of creating two separate risk maps for each vehicle type?
That's a good question. I don't know. I think that what I would say is that we're going to enter this hybrid world in two ways. One is that the world's hybrid because there's a mix of vehicles. That's hybrid. But the other part of it is it's going to be hybrid even in a single vehicle, where there's going to be times when the human is in control. There's going to be times when the computer is in control. And there's probably times when it's partly human and partly vehicle in control. And both aspects of that are important to understand and model. I think there's certain types of interventions that I would have thought on the face of it were non-controversial and obvious. For example, automatically braking when you're about to have a collision. To me, that seems like, why not? It's a great idea. But yet, if you think deeper about it, it's possible that because no technology is infallible, if you mandate, for example, that every vehicle should guarantee with very high probability that it'll avoid collisions, the way you would end up designing this is to also brake when maybe it's not a collision, but you're not sure. The technology is not sure. So it's going to brake more often. Because if the requirement is you have to prevent 99.9% of collisions, then one way you could do this is to brake all the time.
Yeah.
Of course, that's an extreme, but I produce that as an example to say that such a requirement may cause much higher degrees of abrupt braking, but that could lead to more people hitting the car that's braking and the braking could happen quite abruptly because the thing that humans have to, we all know this, computers are blindingly fast relative to humans. And they also make mistakes because if we believe that it's infallible, then what we are assuming is, number one, that sensors are infallible. We're also assuming that software is perfect. And we're also assuming that we can totally understand like the AI is perfect. None of this stuff is true. Sensors aren't perfect, AI isn't perfect, and software is certainly not perfect.
Maybe it just needs to be better than us, though.
Well, but that's the thing. In order for it does need to be better than us, and I think it is better than us. But the better than us cannot be viewed in isolation. It has to be viewed in combination with how does that make the other humans on the road respond? That's the holistic systems like type thinking that's critically important. Because for me to have an autonomous vehicle that reacts in 10 milliseconds and brakes to avoid every collision, that's one part of it. But that could cause other people to not respond so quickly, leading to an overall worse outcome.
So it just occurred to me, it seems kind of silly that I didn't think of this earlier. Earlier on, we're talking about we can model, like put a speed bump here, what's happening. Could you introduce a different fleet into I don't know, a road network? Could you say what would happen if, I don't know, 40% of all of these vehicles were autonomous?
Yeah, you could. Unfortunately, the way these methods scale is you have to have enough data where you understand and can draw those inferences. And I suspect some of the AV companies like a Waymo, Tesla, Tesla's not quite AV, but they have a lot of data that goes into AV. And those companies might have the data that together with other sources of data could provide this. But I'm not so sure they have the scale in the variety of conditions
Mm.
that we can draw. For example, what happens in a snowstorm in, Rochester, New York?
Mm.
The conditions are quite varied, and you need enough data for these methodologies to be used.
Could you go through your data set? Because there must be some sort of vehicles that are driving around that have your chip in them or your sensor in them that have some level of autonomy. Can you go through and find those and say, okay, let's start modeling these things here?
Yeah, that's the sort of thing we're actively working on. I'm not so sure we have enough of that data yet. Yeah, we don't. And I think even modeling AVs is hard because no two AVs are the same.
Mm. Yeah.
And we don't have enough AVs right now to draw this data at scale, but I think we will at some point.
Yeah.
But I do think that's the type of science that's important to take on, just like what happens with infrastructure changes. What happens if 20% of the vehicles are autonomous or have a different type of technology? Because it is a systems problem, not an individual vehicle problem. That's one of the messages that I think it's important for all of us to, whether you believe it or not, I think it's important for people to acknowledge and appreciate that it's a possibility, that it isn't about keeping the individual vehicles safe. Do you know that 50% of the people impacted by vehicle crashes today are outside the vehicle?
No.
50% of serious crashes, it's about 20% in the US, it's about 50% worldwide.
Wow.
They're not in the car, they're
Yeah.
outside the car.
Yeah. I guess like being a non-expert and talking about this, you have these assumptions, right? Of course, it's about keeping the car safe in the other car. Of course, it's about like things are going to get automatically better when we introduce more of these vehicles on the road because they'll be smarter, faster, better, all that kind of great stuff. But yeah, it's definitely not as clear cut as what I imagined before we started this conversation.
Yeah, and I'm not skeptical of this. I do think it's genuinely going to be better, but I think it's going to be better if we think about this as a broad system rather than something in isolation. It's not sufficient to say, hey, my car had a lower crash rate that I was responsible for,
Mm.
because it could lead to other people, other users having, or other vehicles having different crash rates because of the decisions that the computer made.
Yeah, yeah. I'm sure there's a ton more to talk about in terms of this. But I want to round off the conversation. And because this is a geospatial podcast, all of the stuff we've been talking about has a relation to geospatial, to location. But I want to round off with this question that I think you might be able to offer some really interesting insights around. Will autonomous vehicles need better maps than what we have today? And like better maps than what humans need? Or the maps we use today, it works. I mean, definitely it could be better, but it works. We get around. Transportation happens. Will autonomous vehicles need better maps, or can they make do with what we've got now, or will the maps need to change in some way, shape, or form?
Fundamentally, I think it is helpful for autonomous vehicles to have good information on map data. I think the type of things that probably would make the biggest impact on them in the near term is ready access to more dynamic information,
Hmm.
sort of real time information. For example, when an infrastructure change has occurred, being able to leverage map, dynamic data to improve those maps. And the second thing that I think they will benefit from is the type of work that we're doing at CMT, which is providing information about the pattern of driving at large in any given area in a highly granular way. Here's how regular vehicles drive. And that can be used to adapt for these autonomous vehicles to adapt to the driving culture of the place, which I think is important. It's important to adapt to just like human beings adapt to driving culture. They drive a little differently when they're in different areas. Even when it's new to them, they figure out how other people are driving and adapt to that. I think having that knowledge from dynamic maps, when I say dynamic, it's layered on top of the maps, would be helpful. But the types of questions you might be asking are related to the precision of the maps and the exact number of lanes and so on. And I think there are two schools of thought on that. I think it doesn't hurt to improve it, but I don't think that AVs, in order to just stick within a lane or whatever, need that. I think they will adapt using their own local sensors to whatever's happening, because human beings don't have very detailed knowledge of maps, like at the level of precision. I mean, we sort of figure it out because of perception. And I think perception can help. But where human beings also figure out is we understand the intent, we understand how people are driving on these roads. And I think computers with short-term perception, short-range perception, don't have that knowledge. And dynamic maps of the kind I talked about could provide that very valuable information and also allow our AVs to drive the way the best human drivers in any given area drive, because that to me is a good gold standard. Because the best human drivers are really good. There's a few of them, not that many, but they're really good.
That is fascinating. So I was, like you said, stuck on the idea of precision of geometries, for example. I was stuck on the idea of when you're saying real-time updates, I was like, oh, the signpost has changed, the speed limit has changed. But it sounded to me what you're saying, real-time, the risk is changing, the other drivers around you are driving like this. This is the culture, this is the patterns that you can expect in this region.
Yeah, I think so. I think a lot of driving is about expecting the unexpected and responding. And so, put it this way, if you don't have very precise map information, do you want the vehicle to fall off the cliff? No, you want it to adapt, you want it to drive. So from that standpoint, as it's almost like an end-to-end argument, I wouldn't want to build my system to be highly dependent on highly precise maps. I'd want to have much different types of information about maps, but I want the stuff to do well, even in the absence of highly precise information, because requiring that, mandating that, and requiring that would make it extremely difficult to roll it out. And then when it's not available or it's wrong, you don't want it to fall off a cliff. I don't mean literally fall off a cliff. I mean in terms of its performance. That would not be a good system design. So in other words, it's nice to have, but I don't want it. I don't believe it's a must-have.
Hey, I want to be conscious and careful with your time, and we've been talking for a while now. But I've found this fascinating. I've really appreciated the discussion. It's really eye-opening. Thank you very much for coming along and talking with me today. Really appreciate it.
Thanks for having me, Daniel. I enjoyed it, and maybe we can do another one.
Yeah, I'd love to. Where can people go if they want to reach out to you? Are you available on any social media channels? Can we drop some links in the show notes where people can check out some of the work that you've been doing?
Yeah, I think LinkedIn would be good. And our company's website is cmt.ai. That and my LinkedIn would be great. So we can send you my LinkedIn.
Wonderful. I really appreciate that. Thank you again for your time. This has been great. Cheers.
Great. Thank you, Daniel. Bye-bye.
I really hope you enjoyed that interview with Hari, founder and CTO of Cambridge Mobile Telematics. There will be links to where you can connect with him in the show notes of this episode, and also put links to other relevant podcast episodes in the show notes. So please take the time to check them out. Thank you very much for listening all the way to the end. It's much appreciated. I'll be back again soon. I hope that you'll take the time to join me then.